Yeah, in my last class, I discussed various types of pulse width modulation techniques. One of them being harmonic elimination technique. This method says that if there are n switchings per quarter cycle, n minus 1 harmonics can be eliminated and fundamental can be controlled. In the last class, I did give an example wherein there were 5 switchings. So we eliminated 4 harmonics. There were 5th, 7th, 11th and 13th, and we control the fundamental. See, with 5 switchings per quarter cycle, you can have altogether different fundamental. See, in the last class we got maybe around 0.985 or something like that. We can get much less than 0.985, okay, and still you can eliminate these harmonics, okay, because when we write those 5 equations, you equate 4 harmonics to be eliminated to 0 and control the fundamental. Another observation that we made was at any given time there should not be simultaneous switchings of devices of other phases. In other words, only one phase should be switching at a time. Okay. This is not ensured in the PWM techniques that you have studied so far, okay, because these PWM techniques, they treat one leg of an inverter as an independent unit, okay. So therefore phase voltage is generated independently, or pole voltage is generated independently, whereas the space vector PWM technique, it treats the entire 3-phase inverter as an one single unit, okay. The space vector PWM technique treats the entire inverter as a single unit. In this PWM technique, you will find that at any given time only one switch is being turned on or off. In other words, one leg of the inverter is being switched. Other remaining two phases are untouched at that particular time. Okay. So I did define the space vector. So what is space vector? Vs is given by this equation, Vin plus Vbn e to the power j 2 pi by 3 plus Vcn e into e to the power minus j 2 pi by 3. Okay. I told you that these 3 phase vectors can be represented by a space vector Vs, and this space vector can be represented in 2-dimensional plane, okay, xy plane, wherein Vx is the x-axis component of, or sum of all the x-axis components of these 3 vectors, and y is the sum of all the y-axis components of these 3 vectors. Okay. We resolved these 3 vectors along x-axis and y-axis, and we found that Vx is 3 by 2 times Van, okay, and Vy is root 3 by 2 times Vbn minus Vcn. Okay. We also found a simple relationship between the phase voltages and the pole voltages, okay, because when the inverter is being switched, the pole voltages are known, but then the phase voltages are not known. Okay. We found that matrix to be very simple one. See, Vin, Vbn, Vcn is equal to 1/3 See these elements, diagonal elements are 2, rest all are minus 1, minus 1, minus 1. VA 0, VB 0 and VC 0. So, if the conducting state of the inverters, upper devices of the inverter are known, that is 1, 3, 5 or SA, SB, SC, so VA 0, VB 0 and VC 0 will be known. Okay. When upper switch is on, it is VA 0 is plus VDC by 2. If the lower switch is on, it is minus VDC by 2. So I can calculate VIN, VBN and VCN. In the last class, I did derive or I did find the value of the space vector for 0, 0, 1 vector. What is 0, 0, 1? I took upper device of phase A is on, upper device of phase A is on and lower devices of phase B and phase C are on. Okay. So, for SA1 or upper device of A phase is on and lower device of phase B and phase C are known, we found that the magnitude of the space vector is the magnitude of the entire DC link, the whole DC link VDC. Okay. It has only an x-axis component. Okay. Y-axis component we found that it is to be 0. So angle happened to be 0. Okay. So it is along, Vs is along the x-axis with the magnitude VDC. So for 0, 0, 1, if it is VDC at an angle 0, okay, I told you that for 1, 1, 0, the complementary of this vector should be same magnitude at an angle pi. Okay. I told you, if you are not convinced, I said go back and do this exercise. I hope you have done it. Okay. And for the 0 vectors or null vectors, wherein all lower devices are on or when all upper devices are on, magnitude of the space vector is 0 and angle is also 0. Okay. So in the xy plane, this is at the origin. Okay. So if upper 3 are on or upper 3 are off, the space vector with the magnitude 0 is at the origin. Okay. Now what about the remaining 4 vectors? I said 2 to the power 3, there are 8 possible combinations, out of which 2 are null vectors, and we already determined the magnitude and the position of the space vector for 2 vectors, 2 active vectors. Why they are active? Because the magnitude of the space vector is non-zero. We found that for 0, 0, 1 and 1, 1, 0, the magnitude is VDC. Okay. So what is the magnitude for the remaining 4 active vectors? Say I will take 0, 1, 1. That means A phase upper device, B phase upper device, they are on, and C phase lower device is on. Okay. So VA0 is equal to VB0 is equal to VDC by 2, because upper device is on, whereas VC0 is minus VDC by 2. Okay. Now if I substitute these values in that matrix, we will find that VIN is equal to VBN is equal to 1/3 VDC. Okay. And VCN is minus 2/3 VDC, because it is lower device is on. Okay. So from the switching position, we could determine VIN, VBN and VCN. Now these 3 vectors are known, so I can calculate Vx. Vx is nothing but 3/2 times VIN. Okay. So Vx is half VDC, and Vy is given by root 3 by 2 times VBN minus VCN. So that is equal to, you substitute these two values, you will get root 3 by 2 into VDC. Okay. Now what is the space vector? Space vector Vs is Vx plus j into Vy. Okay. Vx is half VDC, Vy is root 3 by 2 times VDC, and it is positive. So Vs is, I can substitute this for that equation. For Vs, this is what I get, half plus j root 3 by 2, half plus j root 3 by 2. Real component is half, imaginary component is root 3 by 2. So again, the magnitude of this is 1, okay, at an angle 60 degrees. Cos 60 is half, sin 60 is root 3 by 2. Okay. So therefore, for 0, 1, 1, the position of the space vector is at an angle 60 degrees with respect to the x-axis, 60. Magnitude is the same, VDC. Okay. So for 0, 1, 1, the magnitude of the space vector is VDC at an angle 60 degrees with respect to x-axis. For 1, 0, 0, which is the complementary of the previous vector, the magnitude of the space vector is still VDC, but at an angle 60 plus 180, that is at 240 degrees. Okay. So that's what I have written here. For 1, 0, 0, okay, Vs is VDC at an angle 240. Okay. So we found the position as well as the magnitude of the space vector for 4 active vectors. The magnitude happened to be the same. Now only the angle, the position of the space vector seem to be changing. Okay. So we will find out for one more case, and I can use the complementary of this vector, and I can get the position of the space vector. So the last one being 0, 1, 0. Only upper device of B phase is on, A phase is off, and C phase is also off. So therefore Vs0 equal to Vc0, both upper devices are off, so magnitude is minus half VDC, okay, and Vb0 is plus half VDC. So what will be the VIN, VBN and VCN for this combination? A phase is also off, C phase is also off. So VIN is equal to VCN, that is equal to minus 1/3 VDC, okay, and VBN is equal to 2/3 VDC. Okay. Straight away you can write, you don't need to write, substitute this in that matrix. See, for 0, 0, 1, we found that VIN is 2/3 VDC, and VBN and VCN are minus 1/3 VDC. So in other words, if only one switch is on, I will repeat, if only one switch is on, the magnitude of that voltage is, magnitude of the phase voltage is 2/3 VDC. Okay. If two switches are on, magnitude of the phase voltage is 1/3 VDC. The sign depends on whether it is upper device or lower device, that is all. Okay. If lower device is on, it is minus, if upper device is on, it is plus. That is the sign convention. Okay. So I will repeat, if only one device is on, magnitude is 2 by 3 VDC of that phase, and the remaining 2, it is 1/3 VDC. If 2 are on, magnitude is 1/3 VDC. Okay. The sign depends on whether its upper device is on or the lower device is on. So what is Vx now? Vx is given by 3 by 2 times VIN or 1.5 times VIN. Okay. So Vx is minus half VDC. I will substitute for VIN. So Vx is 0.5 VDC and Vy is root 3 by 2 VDC. Okay, I will substitute for VIN, I will substitute for VCN and VBN. So it is again root 3 times VDC. So therefore the space vector is minus half VDC plus j root 3 by 2 times VDC. So again minus half plus j root 3 by 2, magnitude is 1, but then angle is 120 degrees, cos 120 is minus half, sin 120 is root 3 by 2. So therefore the position of the space vector for 0, 1, 0, it is at 120 degrees with respect to the x axis. So therefore for 1, 0, 1, okay, it is 120 plus 180, that is at 300 degrees. So it is here for 1, 0, 1, Vs is VDC at an angle 300 degrees. Okay. So for all the remaining 6 vectors, we found that magnitude of the space vector is the same. Okay. Now let us plot these 6 vectors, in fact all 8 vectors in the xy plane. What sort of a figure that we get? See, 0, 0, 0 or 1, 1, 1, we are at the origin. Okay. 0, 0, 1, only phase A is on. Okay. So magnitude is VDC and it is along the x axis. Angle is 0. For 0, 1, 1, vector is making 60 degrees. Okay. And for 0, 1, 0, vector is making 120 degrees and so on. Okay. So if I try to, because all the magnitudes is, all the sides are of magnitude VDC, okay. So I can join them, so I get a hexagon. Okay. So what conclusion that I can draw? Out of 8 possible vectors, 2 are null vectors which are at the origin. The remaining 6 are at, or the angle between any 2 vectors is 60 degrees, and all the 6 vectors, they occupy the vertex of a hexagon. See here. Okay. 6. I am calling these vectors as V1, V2, V3, V4, V5, V6. Please, these are not the binary equivalent. Okay, I am just calling as V1, V2, V3, V4, V5, V6. V0 and V7 are at the origin. Okay. See, now take the pole voltages for 180 degree conduction, VA0, VB0 and VC0. for each position or for each active vector, okay, the space vector is occupying one of these 6 places, one of the 6 places. See, for example, see, it is A phase is 1, B phase is 0, C phase is 1. So, if I take 1, 0, 1, where are we? Here, 1, 0, 1. Okay. See, next is 1, 0, 0. Okay. A phase is 1, B phase is 0, C phase is 0. So, this is pi by 3, that is 60 degrees. Another 60 degrees we have A is 1, B is 0, C is 0. So, we are here. Okay. What happens from 2 pi by 3 to pi? A is 1, B is 1, C is 0, C is 0, C is 0, B is 1, A is 1. Okay. So, V2 vector. Okay. Definitely, see, next is, I will just repeat for one more. A is 0, lower device is on, B is 1, say for another 60 degrees, another 60, before BC0 becomes 1, 0, 1, 0, 0, 1, 0, see, we are somewhere at this point. So, even if I use 180 degree conduction, in other words, each device is conducting for 180 degrees for each positions, okay, I have a space vector, the magnitude remains the same, okay, but the position shifts by 60 degrees. Okay. Now, if VIN, VBN, VCN are sinusoids, okay, VIN, VBN, VCN are sinusoids, so I can write the space vector Vs as m into e to the power j omega t. In the 2-axis plane, Vx plus jy we wrote. Now also I can write that Vs is m into e to the power j omega t, where m is some modulation index and omega is the frequency of VIN, VBN and VCN, which is same as the frequency of the space vector. What is the locus of the space vector? If VIN, VBN, VCN are sinusoids, okay, what will be the locus of Vs? Locus of Vs is a circle, Okay. So, what should be the ideal locus or trajectory of Vs? I said we need to have ideal 3-phase sinusoidal voltages. So, only then maybe when I apply them to a machine, a 3-phase balanced load, it will draw a sinusoidal current. But then unfortunately it is just not possible to have a pure sinusoids, but then it is always desirable to have these 3 as sinusoids. So, if these 3 are sinusoids, locus of Vs is a sinusoid. Okay. So, therefore, the locus of Vs is sinusoid if the magnitude of Vs is less than the diameter of the inscribed circle. Okay. Or in other words, if magnitude of Vs lies within this hexagon or within this circle, okay, if it lies within this circle, I have VIN, VBN, VCN are sinusoids. Okay. But then if I use 180 degree conduction, at every 60 degrees one switch is being turned on or off here. Okay. We find that the space vector moves by 60 degrees. See here, A was on, B is off and C is on. We are here. Maybe after 60 degrees when I turn off the upper device of C phase, immediately we jump here. Our space vector jumps here. When after 60 degrees B phase is being turned on, the space vector jumps here. Okay. So in one cycle is completed after 360 degrees. In fact, there are 6 combinations. The space vector moves in discrete steps. Remember, the space vector moves in discrete steps of 60 degrees. Okay. So when you apply this space vector to a machine or these voltages to a machine, the field produced by this space vector Vs also moves in discrete steps of 60 degrees. See, after all, these voltages are being connected to the machine. Okay. We are generating 3-phase voltages, okay, and they have to be connected to the machine, and we found that at every 60 degrees one switch is being turned on or off. So the space vector is moving in 60 steps. A space vector is moving at an angle by an angle of 60 degrees. So there definitely the magnetic field, the resultant magnetic field produced by this space vector is also moves in steps of 60 degrees. So definitely the magnetic field produced doesn't rotate at a uniform velocity inside the air gap. It moves in discrete steps. Okay. See, here is a pure sinusoid. That's what we want. Call it as VAN. If we use 180 degree conduction, VAN has 6 steps per cycle. There are 6 steps, each of 60 degrees. Height is 1/3 VDC, 2/3 VDC, again 1/3 VDC. Now, of course, it is rather impossible to get a pure sinusoid. Okay. Can I increase the number of steps and try to achieve a sine wave which is very close to the sine wave? In other words, can I have a large number of steps in one cycle? Okay. It's something like this, digitizing a sine wave, in the sense have a large number of steps in half a cycle. So similarly in the negative half cycle. See, if you give this sine wave to a ADC, how do I digitize it? Digitizing means I have an analog signal, I need to convert it into a digital signal. So I need to give to an analog to digital converter. Now this analog to digital converter has its own conversion time. Okay, it cannot. There may be a very fast ADCs, but definitely conversion time cannot be will not be 0. It has a finite conversion time. So what I'll do, the ADC will sample it, sample the instantaneous value of the sine wave, convert it to an equivalent digital value, and depending upon the sampling frequency, okay, the ADC digitizes the given analog signal, okay, and then if I plot it, I get a stepped sine wave, because for this time, during the sampling time, okay, we are assuming that sinusoid does not, a value of the instantaneous value of the sine wave does not change, it remains constant. Okay. So larger the number of steps, better will be the sinusoid, or waveform is superior. Okay. So definitely I need to have a large number of steps, or in other words, I need to sample this sine wave at a very fast rate, and what will assume, and in that sampling time the instantaneous value of the sine wave remains constant, and the vector, the reference vector or whatever the sign vector, is stationary at that particular point. Okay. So now how do I generate the required space vector of some frequency and magnitude? Who decides the magnitude of the space vector? It is the load, or the V by F curve decides the magnitude of the space vector. Okay. After all, is an inverter, it is being switched using a space vector PWM technique. Output of the inverter is connected to a load. Okay. And how do I decide the frequency? The time taken by the space vector to complete one cycle decides the frequency of operation. Now how do I generate this space vector of some magnitude and some frequency? Because we found that there are only 6 active vectors, magnitude of the space vector is constant, and for every position space vector moves by 60 degrees. I told that this is not acceptable. Then I showed that the sine wave should be digitized. Okay, I cannot have a continuous sine wave, that's not possible. Best way to have is you divide a half cycle into large number of steps. But here is an inverter where there are only 6 vectors are available. Now how to get this space vector of required magnitude? Now let me recall one of the qualities that a good PWM technique should have. What is that? At any given time, the switches of one phase should change its state. In other words, there should not be a simultaneous switching of other phases also. And I told you that space vector does this. How the space vector manages to switch one switch at a time, or how this is being done? So here is a philosophy of the space vector PWM technique. What it says is, if the space vector lies in between any 2 vectors, okay, if it lies in between any 2 vectors, you need to use only these 2 active vectors and the 0 vector to synthesize the space vector of required magnitude. I will repeat. If the space vector lies in between any 2 vectors, at any given time if it lies in between 2 vectors, we need to use only these 2 vectors and the 0 vector, or at the origin, to synthesize the space vector of required magnitude. Okay. Okay, I will give an example. Assume that Vs star, in the sense I put a star here because the magnitude is very small compared to the VDC, because depending upon V by F or depending upon the frequency of the space vector, magnitude also changes in order to keep V by F constant. Okay. Looks like the frequency of operation is less than the rated, therefore the magnitude of the space vector is also less than the rated, and it is lies in between sector 1 and sector 2, or it is in sector 1. I am calling, okay, I just may not have explained. See, this is sector 1, sector 2, sector 3, sector 4, sector 5, sector 6. Okay. So please remember, sector 1 is from 0 to 60 degrees and sector 2 is 60 to 120 and so on. Okay. So therefore I assume that the space vector lies in sector 1. Okay. Now, and the magnitude of space vector is less than the rated. How to synthesize this vector? The condition to be satisfied is that there should be a volt-second balance. I will repeat, there should be a volt-second balance. By the way, what is this volt-second? Volt-second is nothing but flux or incremental flux, because d phi by dt is equal to E. E is the unit of E is volts. So volt into second is nothing but d phi. So therefore, see, here is a space vector Vs. When it is applied to a machine, definitely it produces some flux at some direction. See, I am not going to discuss about the direction of flux produced by Vs. Okay. Now I have to synthesize this Vs using these three vectors, two active vectors and a null vector. And I said volt-second balance should be there. In other words, incremental flux produced by Vs or flux produced by Vs when it is in this position, should be same as the flux produced by the space vector when you are in this position and this position. Okay. I will repeat, the incremental flux or the flux produced by, or total flux produced by the space vector when it is in this position, magnitude and position both should be same as when you switch this as well as this. See, when V1, when I am switching 0, 0, 1, or when you use this vector, the space vector is along x axis and magnitude is again constant VDC. Okay. So definitely it will produce some flux or incremental flux, the direction again definitely different from the direction of incremental flux produced by the Vs or required position. I will repeat, see, when you switch 0, 0, 1, space vector is along x axis, magnitude is VDC. Okay. So incremental flux again depends on the position of this vector. When I apply this, the position is going to be different. Magnitude of VDC is constant, or magnitude of space vector is equal to VDC, which is constant. So direction of incremental flux when I apply this vector and this vector, they are different. Okay. What I want is here the Vs vector, the net effect should be the same as the space vector, volt second of the space vector. Okay. So I will repeat. So therefore, if V1 is applied for some time, say t1 seconds, and V2 is applied for some seconds or some t2 seconds, and 0 vector for tz seconds, what is the volt second balance condition gives? V1 into T1 plus V2 into T2 plus Vz into Tz should be equal to Vs into Tc, some time Tc, which is equal to the sampling time by 2. Okay, sampling time by 2. So we have assumed that Vs, the position as well as the magnitude, will remain constant during this time Ts, or during Ts time. Okay. So during Ts seconds, Vs is at this position and is held and assumed to be stationary with constant magnitude. Okay. So definitely Vs into Tc is the incremental flux. Okay. That I need to get by switching V1 for some time and V2 for some other time and using this. But then in this equation, Vz into Tz is 0 because 0 vector. Okay. So the vector itself is 0, definitely incremental flux also will be 0. Okay. Now how do I determine, or how do I calculate T1 and T2? I said volt second balance has to be satisfied, or if this is the resultant, okay, or this is what is to be synthesized, or this is the incremental flux due to the space vector in Tc seconds, somehow I need to get using these two vectors. Okay. Now say when I apply V1, I am along the x-axis. Okay. It has no y-axis component. When I apply V2, it has x-axis component as well as a y-axis component. So what I will do is, I will add up the x-axis components as well as y-axis components. The resultant should be equal to Vs into Tc. See here. So therefore, the sigma, the sum of x-axis components of the right hand side, what is that? Right hand side, magnitude is Vdc into T1, because I am applying V1 for T1 seconds. So Vdc into T1 is the x-axis component. Okay. Vdc into T2 into cos 60 is the x-axis component of V2 into T2. So here Vdc into T2 into cos 60, okay, is equal to, the sum is the sigma x of the right hand side. What is the sigma x of left hand side? See here, it is Vs into Tc, okay, and angle is theta. So this is it. So Vs into Tc into cos theta is a sigma x of the left hand side. So I need to equate them. Okay, x axis components are same, y axis components are same, therefore definitely I have synthesized the space vector. Okay, so T1 plus T2 into cos 60 is equal to A into Tc divided by into cos theta. Okay, where A is Vs star into Vdc. See, I need to equate this equation on this. Vs star into left hand side should be equal to the right hand side. So T1 plus T2 cos 60 should be equal to Vs star divided by Vdc into Tc into cos 60. So I have one equation. Similarly, I will equate the y axis components. Okay. So y axis component is Vs star into Tc into sin theta should be equal to Vdc into T2 into sin 60. See in this figure, y axis, this has no y axis component, whereas V2 has both x as well as y axis components. So V2 into sin 60 into T2. Okay. So therefore T2 sin 60 equal to same Vdc divided by, sorry, I will equate them. So T2 sin 60 is equal to Vs star divided by Vs into Tc into sin theta. So I call it Vs star by Vdc as A. So T2 sin 60 is equal to A into Tc into sin theta. So T2 from this equation, T2 is equal to Tc into A into sin theta divided by sin 60. I will substitute this, or substitute the value of T2 in this equation and solve for T1. Okay. So I will get another simple equation. T1 is equal to Tc into A sin 60 minus theta divided by sin 60. What is theta? Theta is the position of the space vector in the xy plane. Okay. So see, only theta should be known here, position. The magnitude of the space vector that should be realized is known from the V by F curve. Vdc is also known. Okay, therefore A is known. Tc is the sampling time, that is also is decided. Again, so I need to know the position of the space vector in the xy plane. So if I know theta position, I know T2. I can calculate T1. Okay. So T1 and T2 are known, so remaining period should be Tz. That is nothing but Tc minus this. So it is, so time for which vector V1 and vector V2 should be applied can be determined if I know the position of the space vector in the xy plane. That's all. Okay. So what are the observations that I can make from the analysis that I did so far? Tz or zero vector period is given by this equation. Okay. It could be, or Tz could be realized using either 0 0 0 or 0 vector or 1 1 1, okay, or both. Okay, it does not matter, because voltage the magnitude of the space vector when I apply these vectors is 0. So Tz could be 0 0 0 or 1 1 1 or I can use, depending upon the suitability, I can use any one of them. So I will make another statement, irrespective of the ratio in which Tz is divided between the 0 states. I said this could be either this or both. Okay. The average voltage vector produced is the same as long as Tz is as per the above equation. I will repeat, what does it mean? In what ratio you divide the 0 vector into this and this, it does not matter. I will repeat, in what ratio you apply 0 0 0 or 1 1 1, it does not matter, as long as you satisfy this equation. Okay. So if you satisfy this equation, it is doesn't matter how long you use this or this. Okay. And what is the second observation? I said active vector V1 should be applied for T1 seconds and vector V2 should be applied for T2 seconds. Okay. So I am not saying that V1 should be applied in a continuous interval of T1 seconds within a subcycle. So it means this, that you do not need to apply V1 continuously for T1 seconds. Okay. You can divide this T1 seconds in as many parts that you want, okay, but that should be within a subcycle. Is that okay? Okay. So V1 need not be applied continuously for T1 seconds. You can divide T1 depending upon what sort of a harmonic spectrum that you want, because there are large number of different PWM techniques that have been proposed by dividing this T1 period into a large number of different parts. Similarly is true for the V2 vector. Okay. So more about it I will explain in the next class. Thank you.